The real physics is created anyway. Yeah, so they're actually taking it.
That was wild, isn't it?
Okay, let's review quickly what we reviewed last time in our review. First of all, we talked about work briefly and just said work can be thought of as a process. Okay, hold it down please so everyone can hear it. Work can be thought of as the process of converting energy from one form to another, or actually moving energy from one body to another. We talked about how young you all are, and that you don't get the joke. And forces can do work. I assume you did all of this before I even showed up. We talked about a force field. We considered a force field that had no external source of energy. It just sort of sits there and it always exerts its force, like a compressed spring or a static electric charge. And we asked the question, is the force field created by such a system conservative? And that means, does it allow me to get an endless amount of energy from it? Well, if there's no external source of energy, we expect that to be no, you can't get an endless amount of energy from nothing, because we have a big energy problem in the world, and so that wouldn't be a problem if we could get all we wanted for nothing. And then does it have a potential field to go with the force field that would be related to it? We talked about that objects do not always move in the direction of the force that's applied to them. Anybody who's ever held something in their hand knows that the force of gravity is fairly constant, no matter where you hold it. And yet, if you throw it, it's always down, right? But if you throw it, it doesn't move in the direction of the force. So lines of force are lines of acceleration. They're not trajectories of motion. We talked about if we have this static force field that used no external source, then the work done from point A to point B has to be the same, no matter what path I use. Because if it were different, I could go from point A to point B the easy way, and I could go back from point B to point A and get back more work than I put in to get there in the first place. And then I would end up back at point A with a net gain of energy for free, and that's impossible. We talked about potential energy, which is a way of accounting for the work that a force field will do if we let it. And so we can give a brick or a massive phase gravitational potential energy by putting in work and lifting it up against the force of gravity. But now it's here in the force field, and if I let it drop, that work comes back to me in the form of kinetic energy. So gravity is a conservative field, and conservative fields, all conservative fields have potential energy. Force fields then have this work that we can calculate, and we can construct a potential energy field, which is a scalar field, a scalar function of position, by using the work that the force field does to move a particle from one place to another, say from A to B. We talked about this example, which is one-dimensional motion, say a particle moving on a spring. Right? That's not a graph of a billiard ball on a pool table, which has two dimensions of motion. The vertical dimension is potential energy as a function of the one-dimensional position. When you compress the spring, the potential energy goes up the farther in you move. So as I move to the right in X, my potential energy is going up because I'm compressing the spring. But visually, sort of as a mnemonic, we can say that particles roll down potential hills. Force fields and potential energy is defined in such a way that particles move under the influence, or at least accelerate under the influence of the force field, such that they go downward in potential energy. The force field pushes on the particle and does work on the particle, meaning the potential energy from that force field is being converted into the work and going into the particle as energy. So the potential energy goes down. We said that the work done is independent of time. Work is integral F dot ds. There is no time in that equation. It doesn't matter if the particle is moving fast or slowly. If it moves from A to B in the same force field, it gets the same work done. So work is not only independent of path, it's independent of time. So then we define potential energy more specifically because we figured out a way to compute W, the change in the potential energy between 2 points. But that doesn't define an absolute field, U, as a function of position x, or in 3 dimensions r vector. But we define that function of r vector simply by choosing a reference point, and then saying u of r is equal to delta u from that reference point to the point r. Now u of r is a well-defined mathematical function. It's a scalar function of 3-dimensional space in general. And that means we can take derivatives of it. And by simply differentiating what we got, the way we got u of x, we find f of x is negative du dx in 1 dimension. And the 3-dimensional generalization of that is the gradient operator, which says the derivative of u with respect to x is the x component of the force. This here is f sub x. The derivative of u with respect to y is the y component of the force. This is f sub y. And the derivative with respect to z is, of course, the z component of the force from the force field. That's what we're talking about. So the gradient operator is just a short way to write those 3 derivatives with these unit vectors added onto them. So the gradient is an operator that takes a scalar function of space and produces a vector function of space. U of r is a scalar function of space, f of r is a vector function of space. Okay, this is review, so I'm running through it very quickly. And this is where we stop. There was actually a mistake on this slide last time, and I fixed it. So I will post the new slides today, and you'll get the corrected version. There were some minus signs missing. The final answer was right, but I had some minus signs. So let's do an example of the gravitational potential of a point mass. The Earth is fairly small, so we'll call it a point mass. Okay, it's not really very small, but because it's spherically symmetric, approximately, we will approximate it as a point mass. A perfectly spherically symmetric mass would be represented for all considerations outside the surface of the sphere as if it were a point mass. All of the forces are absolutely identical. We will prove this next quarter in 2B. It's also true for electric charges as well as gravity. So if we make the approximation that the Earth is a sphere and we concentrate all its mass at a point, now we can ask ourselves, what is the potential energy of a spaceship? So gravity, a lot of times when we talk about gravity, we say, oh, gravity is constant, because we mean small-scale gravity. Within this room, gravity is pretty constant. When I walk up to the back of the room, I'm farther away from the center of the Earth, and so strictly speaking, gravity is a little teeny bit smaller, but nobody can really measure that without very precise equipment. We actually use equipment in my research, by the way, that can measure that difference. The gravimeter we use to measure the difference between the gravity on this tabletop and the gravity on the book above the tabletop. We can measure that difference because this here is farther away from the center of the Earth than this tabletop is by about 2 centimeters. So anyway, in a spaceship, you're far away, gravity goes like 1 over r. The force of gravity goes like 1 over r squared. You're familiar with that? Have you seen that the force of gravity goes like 1 over r squared? Okay, trust me on this. The force of gravity goes like 1 over r squared. So if your spaceship is, say, at the position of the moon, roughly 400,000 kilometers from the Earth, there'll be some force of gravity, right? I mean, the moon is held in its orbit around the Earth by the gravity from the Earth. If I were to double the distance of my spaceship, if I were to go twice as far away as the moon to 800,000 kilometers, then the force of gravity would be cut to 1/4, right? Because it goes 1 over r squared. If I double r, the force goes to 1/4. Is that clear? All right, so now we can count. That's all we need to know to calculate the potential energy of some spaceship in the space around the Earth. So we can use a one-dimensional analysis because we'll just imagine that the spaceship is, for our analysis, we will choose a radial line of motion from the center of the Earth out in some direction. Doesn't matter because the whole thing is spherically symmetric. So this is our radial distance. And we don't have to worry right now about moving across the radius, just in and out along the radius. Well, from our standard equation, u of r minus u of infinity, that's delta u, is equal to negative the integral of f of r prime dr prime, where r prime is just the Jones variable integration. So I'm using r prime inside the integral to distinguish it from r, which is the potential at the point we're trying to calculate. Okay? It's the point at which we're trying to calculate the potential. Now we're integrating backwards as well because we choose r equals infinity as our reference point, and this is standard. It's just convenient, although it might not seem convenient. And for some calculations, you would choose the surface of the earth as your reference point. But for big, faraway things, the easiest thing to choose as your reference point is to say, a spaceship that's far, far away from the earth has pretty much no effect of the Earth's gravity on it. And so that's a handy place to just say u is 0. So that's our reference point. Remember, for potential energy, you have to pick a reference point. I mean, strictly speaking, it's not exactly a point, but it's, you can pick some point that's so far away that it might as well be at infinity and that would be good enough. Okay, so that's all we're saying by this. But notice we aren't integrating backwards. We're integrating because we're going to say, what is the work done when I come from my reference point to some distance r? So we're coming from infinity to r, right? So I assume you've all done that in calculus. The limits of integration go whichever way they need to go. In this case, they need to go backwards. That means every little dr prime is negative. Because we're starting big, here's the f of r, but there would be a little dr prime that points this way. Right? But that's handled automatically for us by the lower limit being bigger than the upper limit. And so you'll see that this all works out. The math just works out beautifully, and you get the right answer. So qualitatively, gravity is always attractive, right? And spaceships don't get pushed away by the gravity of the planet. So what is the sign, S-I-G-N, of the potential energy for a spaceship at some finite distance from the planet? Is it positive or negative? It's negative. Why?
Because it's not doing any work. Gravity is doing work on it.
Right. Gravity has done work on it, and so the work done by gravity will be positive as it moves from far away toward that. And that means the force field is giving energy to the spaceship, right? If you let the spaceship fall, it speeds up. It's gaining energy. And so potential energy must be going down. It started at 0 far away and went down from 0, so it's negative. Okay? Remember, smart people ask questions. Stop me anytime. Yes, here's a smart man right here.
So what was the question that you asked before? Is the spaceship starting from far away and then going towards Earth, or going away?
So the question is, which way is the spaceship going? It's starting at our reference point, and we're letting it fall under the action of the force field, in this case, and it's going toward the Earth. And so we're asking for the potential energy at some point r nearer to the Earth relative to our reference point, which is some faraway point.
So it'd be negative as you're going towards...
Right, so the work done is positive by gravity, which means the potential energy is negative.
Okay.
So at some point here, the potential energy is negative. By the way, I've drawn representative force field arrows. The force is strong when you're close to the Earth. The force, that little plus sign might look like a positive charge, but after I stole this slide from 2D. But just pretend like this is yours. And the force is weaker when you're far away, so the force arrows sort of represent that drop off, that 1 over r squared force defense. Okay? Yeah?
Does the spaceship also experience force gravity from other planets?
Yes. Yeah, so the question is, would a spaceship experience a force of gravity from other planets? And other planets are even farther away than the moon, so we will neglect their effect in this simple analysis. But it certainly would. And if you're doing interplanetary stuff like Voyager, then you absolutely have to take that into account. Right? And the NASA guys take that into all that. But we're not quite NASA yet. We'll get there. Okay, any other questions? All right. So now we can do the integral. We have the integral from infinity to r of negative gml over r prime squared dr prime. So this is the force of gravity given up there. Why is it negative? Why is the force negative? Why is there that negative sign there? If my spaceship is here,
because it's moving towards the Earth.
right, the force is to the left. That's a negative force, right? R is positive to the right, R is negative to the left. So that's why there's a negative sign there. So this is just f of r, right? That with its negative sign, and there's still another negative sign out front. And then dr prime. Well, who can integrate 1 over r prime squared? That's r prime to the negative 2. The integral of that is
Negative 2 plus 1, r to the negative 2 plus 1 divided by negative 2.
well, so I add 1 to the exponent, so it's r prime to the negative 1, and then then I divide by that, -1. So it's negative r prime to the -1. So now I have a third negative sign, because I still have these first two negative signs. So 3 negative signs turns into 1 negative sign. And I have GMM, which is just a constant. M is, the big M is the mass of the planet, little m is the mass of the spaceship. But for our purposes, it's just some constant. And we have 1 over r prime, that's r to the -1. We have to evaluate it from infinity to r. So when we do this evaluation, we get 1 over r prime minus 1 over infinity, which is 0. And so we end up with negative GMM over r, which is in fact the gravitational potential energy at a distance r from the center of the Earth. And it's important that's from the center of the Earth, not from the surface of the Earth. Because we shrunk the Earth down to a point, we said in all its mass is equivalent to as if it were concentrated at its center. Okay? And in fact, it's negative, as logically it must be from our earlier question. So, like magic, the math works. Gotta keep track of the minus signs though. Right? The difference between a good physicist and a bad physicist is that a good physicist makes an even number of sign errors, and a bad one makes an odd number of sign errors. So if I graph this, potential energy in the spaceship, I should have called it U of R. This label is actually wrong because the blue stuff is the forces, the pink stuff is U of R. And you see that it becomes negative like 1 over R. And it's asymptotically 0 as we get close to our reference point that's far away. Questions on that? Okay. So this leads us to the idea of conservation of energy, which I think by now you have seen and perhaps been quizzed on. The work energy theorem says in the absence of any other places for the energy to go, kinetic energy final is equal to the kinetic energy initial plus the work done on the body. Work is the process of converting energy. In this case, we would consider the work positive if it goes into our system, whose kinetic energy we're talking about. We have a force field like gravity or electrostatics or a spring. The work done by the field reduces the potential energy and increases the kinetic energy by the same amount. We just said that. So work will be positive if it's done by the field, which means the final potential energy is less than the initial potential energy. But that means the kinetic energy went up by W and the potential energy went down by W. And so the total energy, which is the sum of kinetic plus potential, is KE final plus U final. But that's KE initial plus W plus U initial minus W. It's KE initial plus U initial. The final energy is the same as the initial energy. So if the only forces acting are the conservative forces, and if we have accounted for the conservative forces in our potential energy, then the total energy is constant. That's called conservation of energy. So graphically, we have a big U, we have a little KE. When work gets done, the U gets smaller, and the KE gets bigger. So this leads to the idea of equilibria, stable and unstable, and turning point. Let us consider the graph on the left first, where the blue line is the potential energy field. That means it's derived from a force field. And the force has some weird characteristics, and so we get this shape for the potential energy. Well, we've already seen that particles roll down potential hills. Again, this is one-dimensional motion, right? The vertical scale here is energy, not position. It's just like moving back and forth on a tabletop in a straight line. This is one-dimensional motion. If the particle starts at, say, x equals this 2 point here, the force is to the right because the slope of the potential energy is negative. The particle is going to be pushed to the right. All right? The particle gets pushed in the direction that decreases the potential energy. If the particle were at x equals this fourth position, of course, then it would be pushed to the left. It can, loosely speaking, it rolls down the potential energy, but still in one dimension. Of course, at 1 and 3, the force is 0 because there's no tendency for the potential to change at all infinitesimally for infinitesimal displacements. There is no net force. We have a maximum of the potential energy or a minimum. So we have a zero derivative of the potential energy. The force is zero at those points, 1 and 3. But we can ask, at position 1, what if I poke that particle just a teeny weeny bit? What happens to it? Does it roll back to the point of zero force? If I balance a ball on the top of a circle, and really carefully balance it, and I poke it a little bit, what happens to the ball?
It's gonna roll.
It rolls down. So number 1 is an equilibrium point, but it's unstable. Unstable means if you poke it a little bit, it goes away from the equilibrium point. That's the definition of unstable. Point 3 is also an equilibrium point, but what happens if I poke it a little bit? It rolls back towards the equilibrium point. That's called stable, because it's stable under the influence of small perturbations, right? Small little pokes. So that's the difference between stable and unstable. So this is unstable at point 1, it's stable at point 3. Is that clear? Right? When you try to balance a pencil straight up on its point on the desk, that's unstable. Really hard to do. It's so unstable that it's, for all practical purposes, impossible to do. But if you turn it over on its eraser and it's really smooth and it's really short and it's really quiet in the room, you can balance it on its eraser. And it's just barely stable, right? Yeah, question?
Would there ever be such a thing as a semi-stable point?
Question is, would there ever be such a thing as a semi-stable point? That is an excellent question. And of course you're a smart person because you asked it. It is possible to have a potential that looks like this. And it's actually literally flat out here above some point. And then the question of stability is a little bit trickier because it's unstable to the left. If I poke it to the left, it rolls down the hill. But it's sort of stable to the right. If I poke it to the right, it just sits there. And there's also another case, which would be the case of an inflection point. I could have a potential that looks like, everybody can see this, right? I could have a potential that looks like, x cubed, where it's never horizontal for any finite distance, but I've got an inflection point right here. And that, again, it's sort of stable to the right. And if I poke it to the right, it'll roll back. But if I poke it to the left, it'll fall down. And sometimes that's called semi-stable, because it's half stable and half stable. I mean, realistically, you would have to conclude, like, if you're an engineer building a bridge or something, you would have to say, well, this is unstable. But, mathematically, you could argue that it's semi-stable. Yeah?
Are these stable points by any chance related to the stable and unstable points you work with in a differential equations to find out if there is stable or unstable? Was it by any chance related to that?
So the question is this kind of stability related to the stability of differential equations, where we sometimes talk about differential equations being stable or unstable? I'm not exactly sure what you're referring to in the differential equations thing, and so I suspect that it is, but I would want to ask for more details from you about what equations you're referring to before I could do a definitive answer on that.
Well, I mean, when you're finding out of it point is asymptotically stable. If this is in the same situation or if it's a different one. Because just looking at the graph, the situation seems different. It's not a question of spectrum with physics.
Yeah, let's talk about that afterwards.
Okay.
Because that's an interesting question, I think. So now let's look at this particle on the right. It's the same potential energy. But now we're not going to put a particle at rest. We're going to have a particle that's moving. And we're going to give it some initial energy, say E1. Now, the total energy, E1, since the particle is acting only under the influence of the force field, what happens to its total energy over time? It remains constant, right? That's the conservation of potential energy we said on the previous slide. So whatever's not potential energy must be kinetic energy. So at any point, if we find a particle at some position x, the kinetic energy is the difference between its total energy and the potential energy, right? So if it were here, that would be its kinetic energy. So its kinetic energy and its potential energy both change, but in such a way that the sum is constant. So if I have a particle, say, starting here, it would have some energy, it would have some kinetic energy and some potential energy. From that information alone, can I tell which way the particle is moving?
On the graph, you could tell where it's going to roll.
So I can say which way it's going to accelerate, because the force field goes like that, so it accelerates that way. But can I say which way the particle is moving? Can I say whether it's moving left or right? I know its kinetic energy is this big, I know its potential energy is that big.
No,
Can I say, no, why not?
because the velocity could be really large, but the acceleration can be negative or positive. So it's going really fast in that direction. You can accelerate it to the left, but it's still moving that way.
So the statement is that regardless of the direction of the velocity, I can still be accelerating it to the right.
You can accelerate opposite to the velocity.
Right, the acceleration is independent of the velocity. If I'm moving left and I accelerate to the right, it means I'm slowing down. If I'm moving right and I accelerate to the right, it means I'm speeding up. The kinetic energy is fixed, so what does that tell me about the velocity? It means I can calculate something about the velocity. Can I calculate the actual velocity? No, I can calculate what about the velocity? What?
Average velocity?
Well, this is instantaneous. It's at a point in time. The magnitude. I can calculate the magnitude of the velocity. Ke is 1/2 mv squared. V squared, if v is a vector in 3 dimensions, is v dot v. I can calculate its magnitude, but I can't calculate its direction in 1 dimension. It means I can calculate its magnitude, but I can't tell if it's positive or negative. Yeah, you have a question?
If you know the direction of the initial velocity, particle with the direction of the velocity at a certain point, does that?
So the question is, if I know the initial velocity, can I tell the velocity at some point in the graph?
The direction of the initial velocity. Let's say if you know initially it was this velocity in this direction, then can you tell the velocity at another point with this angular direction also?
Right, so the question is, if I know the initial direction of the velocity, can I tell the direction of the velocity at some point in the future? So let's, no? Is that right? Okay, so let's try that. Let's say I started here, at this point, the initial velocity is 0. Now I tell you at some point in the future the particle is here. Do I now know which way it's going?
Yes. Yeah.
Some say yes. Did somebody say no? Why no?
Because while it will go this way, it could keep going that way, and since we don't know how many times it's gone back and forth, we have no clue at some arbitrary point in the future what it's doing or which way it's going.
Right, so the statement is, certainly at some time in the future, the first time it goes through this point, it'll be moving left. But if I just tell you at some arbitrary time in the future, it's at this point, it might have rolled up the other side and come back again. So without any further information, if all I tell you is it started here at 0, and there's some time in the future it's at this position, you still can't tell if it's going left or right. Because you don't know if it's on the left side slope or rolling back after having reached the left turning point. So that's what leads to the idea of a turning point. Yes?
Are there turning points or points of inflection?
The question is, are the turning points the points of inflection? No, absolutely not. What's the kinetic energy when the total energy equals the potential energy? 0. So what's the velocity when the total energy equals the potential energy? 0. Why is it 0? It was rolling up the hill and now it's 0. What's going to happen in the next instant? It's going to roll back. It was going to the right, it stopped, and it turned around. And now it goes to the left. That's why it's called a turning point. It has nothing to do with inflection. That's a good question. It has nothing to do with inflection. It has to do with the fact that the total energy is equal to the potential energy alone. It's where the total energy crosses the potential energy curve, no matter where that is. Because that's when the kinetic energy is 0. That's when the particle stops, and that's when it turns around. So those those are the turning points. Yeah, question here.
I'm having a hard time conceptualizing a graph based because like the total energy is that dotted red line.
Yes.
But then there's like the potential energy curve goes above that. How is that even possible if it goes above that?
Good question. The question is, if the total energy is this dotted red line, why does the potential energy curve go above that? So the potential energy curve is a graph of, if I force the particle into this position, this is the potential energy it will have. It's not a promise that the particle can ever get there of its own accord. And in fact, when my total energy is at the dotted line, it is impossible for the particle to ever be on at position x, where u of x is greater than e1. And so these are called forbidden regions. Right? When you get to quantum mechanics, you'll find that forbidden regions actually have some probability of finding the particle. So they're kind of discouraged regions. But maybe not really. Yeah.
So if you raise wherever you drop that particle at, that means that if you raise where that particle starts at, then the total energy goes up.
If to raise where the particle starts at, I would have to give it more total energy to start with, and I would have a different dotted red line. Right? But if I say the total energy is this amount, then it means I have to start it in an allowed region. I have forbidden regions and allowed regions. I have to start it either over here somewhere or in this region. But if its total energy is this, I can't start it in the forbidden regions because that violates the total energy. Yeah, question.
Couple of things. One is that, so the ball will basically be moving only between the two turning points, right?
The ball will what?
The particles will only be restricted between the two turning points, right?
Right. If it starts out in this region, it will stay in that region. And in fact, it will have to oscillate back and forth in that region.
And doesn't this assume that the field is uniform? The force field is uniform?
The force field is uniform?
Yeah, if it's not uniform, then you can't say that the total energy remains constant. Because the total energy remains constant only because the force field is uniform. If you have a non-uniform field,
Uniform, you mean it's constant in space?
it's magnitude, and magnitude remains constant with space. If magnitude doesn't remain constant, then that won't hold true.
No. The fact that the potential energy curve is not a straight line tells you that the force field is not constant in space. Right? The force is the derivative of this potential energy curve. The force is to the right, to the left in this region. The force is to the right in this region. It's to the left again in this region. It's 0 here. The force is 0 there. The force is bigger on this slope here than it is on this slope here for the shower. The force is different at every point in space. Total energy is still conserved because any work that's done by the force, regardless of the magnitude, we did the integral of f dot dx. F was a variable, it was a function of x. But still, the integral of f dot dx does some amount of work, and that work goes into the kinetic energy of the particle. So, regardless of the shape of the force field, regardless of the shape of the potential energy curve, if these are the only forces acting, and there's no external force, like my hand, then total energy is conserved. Okay? Other questions? Yeah, up there. I'm sorry, if it starts out what?
If it starts at point Y, why is that total energy curve starts at point 1?
If it starts at point 1, why is the total energy? The graph on the right has nothing to do with the graph on the left. I mean, it's the same potential energy curve, but I'm saying, hypothetically, on the right, I'm telling you that I give a particle an energy E1. And that energy is divided, some kinetic and some potential. But then after that, that's the initial condition. I just let it go under the influence of the force field, and I watch what happens. If I started out in the little bucket there between the turning points, then it must oscillate back and forth between the turning points. What happens if I start it to the right there in the other allowed region? And let's assume that that potential just asymptotically goes to 0 forever. If I start the particle over here at rest, what happens to it? Where does it go?
The velocity will increase towards infinity.
The velocity will increase towards infinity. And when does it come back? Never. That's it, it just goes out. What if I start way out here, and I give it total energy E1 by making it move to the left? I throw it. So it has total energy E1. What does this future motion look like?
It goes up to that.
It'll turn around. It rolls up the hill. This is actually a turning point too, which I didn't label. It'll come to this point X. Remember, it's still one-dimensional motion. It'll come to this point X where it hits this turning point. It's a turning point, so it will turn around. And then it'll go back out to infinity, and it'll never come back. So it'll bounce off once, and then be gone. Okay? Yeah.
So for each point on that graph, so where the ball is, right there, we don't know how long that's going to remain at that certain point on the graph because you don't have time labeled. Is that true?
So the question is, do we know how long it's going to be at this point? Because I don't have time on the graph. Well, in a sense, I mean, I know it's moving because it has kinetic energy. I know the magnitude of its velocity. So it doesn't remain at any mathematical point for any amount of time at all because it's moving. But since I know how fast it's moving, I can tell you how long it's going to stay within some small region around that.
Okay. So then we do know how fast, because you said if you start it on the right turning point, and then you let it roll down, and you just say it's at a certain time t, it is at this point on the graph, you said we won't know its velocity.
Right, if I don't give you that time t, if I just say at some point in the future it's here.
Why, if it just rolls like that?
Right, and so I'm saying at some point in the future I see that the ball is here. But I don't tell you what time I see it. I just say sometime in the future I see it here. Then you don't know which way it's going. If I tell you at t equals 3.7 seconds the ball is here, and if you know the shape of this curve and you know E1, then you can calculate exactly how long it takes to get to that point, and then you would know whether it was going left or right. Right? If you know this potential curve and you know E1, you can calculate the future position of the ball at any point in time exactly.
So we know the magnitude of its velocity?
Yeah, well, if you can calculate its position as a function of time, how would you find its velocity?
Okay.
If you know x of t, how do you find v of t? It's a derivative. It's dx dt. dx of t dt. So if you know its position as a function of time, you know everything. You know its velocity, you know its acceleration.
Okay, because I was just confused because if you have a spring and you let a mass bounce and there's no friction,